Okay, welcome back, folks. This lecture today is all going to be all about band structure diagrams, energy band structure diagrams for electrons in crystalline lattices, of course. And so some of these diagrams, as you might have seen in the textbook, can become quite intricate, complicated, and a little bit intimidating as well. Okay, so for instance, if you go into our textbook here, if you go to page 54, for instance, you see diagrams like this, and they are quite intricate, to say the least, right? And sort of it keeps going here on the next page, and on the next page, still, okay, we get these energy band diagrams. So the question is, what is up with those diagrams? They seem very, very complicated. How should we interpret these diagrams? And one way to sort of approach the whole issue is to look at a special case and try to construct such a diagram ourselves. And in the process of just constructing one of those, we'll get a lot more familiarity and comfortability with them. Okay, so then by doing it, we'll be able to interpret these diagrams as well and get a better sense of what they're trying to communicate. Okay, so that's sort of the game plan for today. So here we are, band structure diagrams. Okay, so we said we wanted to look at an example that's maybe simple so that we can construct one ourselves and see how this is done and get a better sense of what such diagrams are trying to tell us, really. And so a simple example would be to go down to 2D. 1D is too simple, but let's go and look at a two-dimensional system first before we then move to the full three-dimensional crystal. Okay, and also let's look at a square lattice because that is the simplest 2D crystalline structure. Furthermore, to keep things nice and easy, let's also pretend like the electrons are free. So we're going to look at the free electron model. And hopefully that'll be close enough to the nearly free electron model when we turn on a small lattice potential. Okay, so that is the idea. Let's look at that simplest case, really. So the important formula that we have to talk a little bit about is the one that is framed here now. E is equal to h bar squared over 2m times this quantity squared. Now, normally, before we were looking at h bar squared over 2m times k squared. And so that is sort of the energy of a free electron. But in the reduced zone scheme, we have to remember that things can get folded into the reduced zone. And therefore, we have these reciprocal lattice vectors to account for, right? And so now the more generalized version of that previous formula is h bar squared over 2m times the magnitude of k plus g squared. Okay, so where g is a reciprocal lattice vector, and k sort of is the electron state wave vector. We can say that this k sort of indexes the energy state for the electron. Okay, and also the wave vector k has to here remain within the first Brillouin zone, right? We're in the reduced zone scheme. And then, as we said before, g is just any one of the allowed reciprocal lattice vectors. Okay, so how do we construct one of these band structure diagrams? So the idea is to let K explore regions of the first BZ along various paths. So we let K sort of explore, okay, certain areas or certain regions of K space within the reduced zone. And while always keeping track of the energy of that particular K vector. Okay, so for instance, here in a simple 2D square lattice, the first Brillouin zone is a square itself, right? It runs from minus pi over a to pi over a along the x and the y axis, as we've said before. So we'd like to sort of explore this space a little bit, this reciprocal space. And so what we could do is we could start at the origin and then sort of move to the right until we hit the boundary. Okay, and so basically we're just going to move along the x-axis there until we hit the boundary of the first BZ. And then we could say, all right, we're not done yet exploring. Let's go up, okay, until we reach that corner, the corner of the first Brillouin zone. And why don't we make our way back to the origin along a diagonal path, okay? So there we have these three path segments, and we can say that we've sort of explored regions of one quadrant of the first Brillouin zone at least, okay? So we haven't explored the other three quadrants, but you could make sort of maybe a symmetry argument to say that they would be similar. And so maybe this exploration does sort of sample reciprocal space sufficiently. Okay, so that's the idea. We can label these segments, these path segments 1, 2, and 3. Okay, and then let's take a look at path segment 1. Okay, so there we're basically moving to the right in reciprocal space. Okay, and so the K vector then, the associated K vector here is going to be a vector that's pointing to the right. So it's proportional to I hat, the unit vector. Okay, and then we're going to introduce this parameter S that we're going to allow to run from zero to pi over a. Okay, so S is just a sort of a parameter that gives you the length of that vector. Okay, so here I'm having an eye towards a numerical exploration that we'll do in a little bit here. We're going to use Mathematica to look at some of these generated energy bands. And so in Mathematica, of course, everything has to be non-dimensionalized. We can't have units and so on because, well, it's a computer code, right? So here in Mathematica, we'll just let A be 0. We set A to 0 as we have done in the past. And so then S really is just a real number that ranges from 0 to pi and parameterizes that path going to the right. Okay. So then consider different reciprocal lattice vectors. Start with no reciprocal lattice vector. G is equal to 0. That's the simplest case. And then, of course, the energy can be written simply as h bar squared over 2m times k squared, or in this case, since the length of the k vector is just s, we can write it as h bar squared over 2m times s squared. Okay, and so here's our first energy formula. We get the framed equation. Okay, fine. Now let's take a look at the next set of reciprocal lattice vectors. Okay, so G here is equal to plus or minus 2 pi over a times I hat. So those are the two reciprocal lattice vectors that point left and right. So how would we handle that? Well, we can plug that into the general formula and we get this quantity here, right? K plus minus 2 pi over a times I hat. But K itself is a vector that is also basically along the x-axis, right? It's s times I hat. So if I plug that in here, I get an I hat here, I get another I hat here. I can combine that. The magnitude of I hat is just 1. The length of I hat, it's a unit vector, is 1. And so it's not hard to see how we get s plus minus 2 pi over a quantity squared for the energy. Okay, so that'll be another formula, two additional formulas for energy bands. So now, why stop there? We can keep going. So now the next reciprocal lattice vectors that come to your mind are plus minus j, right? The ones that point up and down. Okay, so how would they be handled here? Well, in a very similar fashion, okay, but now we have I hat here and a j hat there. Okay, so there is an x component and a y component, and the vector, okay, that vector is sort of pointing at some angle, okay, and we have to evaluate the magnitude squared of that vector. Well, not very hard to do because we can use Pythagoras, right, because we're dealing with a right triangle of width s and of height 2 pi over a. And so you're not surprised to see that that is the formula we get, s squared plus quantity 2 pi over a squared. Okay, and so here is yet another formula for us. Okay, so we're having so much fun here, so why don't we keep going, right? What are the next set of reciprocal lattice vectors, g vectors? Well, the ones that are pointing diagonally, right? So those are the vectors that we actually already encountered when we tried to construct the first and second Brillouin zones, right? We were basically bisecting these g vectors. And in order to get to the second Brillouin zone and define it, namely those 4 triangles, right, we were basically bisecting g vectors like this, or these 2, and then another set of 2 diagonal reciprocal lattice vectors. Okay, so how do we deal with that? Well, you can convince yourself without too much work that that will be the formula we get for energy. How does that come about? Well, we have an I hat component here, x component, and a y component, a j hat component. So the I hat part of the vector will combine with the k vector, which is also proportional to I hat, okay? And that is this part here. And then we still have the y component of the g vector to account for, okay? And so that is this piece here. And so we get E6, 7 that way, okay? So those were those diagonal reciprocal lattice vectors, okay? Now, of course, the other 2 diagonals are given by I hat minus j hat plus minus out front. And when you combine that with k, you see that you get the same energy formula as is already written here. So there's nothing new along this path, at least. Okay, so all of this was just for path segment 1, okay? And so, but also notice that E4 and E5 were the same, okay? Same energy formula, and 8 and 9 was equivalent to 6 and 7, so nothing new there as well. So we only get 6 separate traces, okay? Because we have some duplication. So we only get 6 energy curves that are associated with path 1. So now we have to repeat it all for the other paths. Okay, so path 2, for instance, well, think about what the k vector would look like. Now we're sort of already at the rightmost edge of the Brillouin zone, and now we're heading up towards the corner of that zone. The k vector would have to look like this, wouldn't it? Here's a constant vector pointing right, and then this gets us to the right edge of the Brillouin zone, and then this gets us to the corner, right? And t here runs from 0 to pi over a. So when t is 0, we're basically where we ended on path 1. Okay, when t is equal to pi over a, well, we've arrived at the corner. Okay, so t then again parameterizes that particular path. All right, so with an eye towards Mathematica, we can write this k vector also as a row vector pi over a comma t, a little bit simpler that way. And now we would have to run through the same set of g vectors that we saw before to generate the associated energy curves. Okay, so I don't want to do that by hand. I kind of would like to use a computer program to do that for us. So that's what we're going to do. Okay, so here we are now in the Mathematica environment. Okay, and so I have sort of pre-formatted this so that we can move through this fairly quickly. In the synchronous part coming up on Friday, we're going to go a little bit more slowly through this, more step by step. But here I just want to give you the bigger picture. So what I'm doing here is, well, we said that we needed to non-dimensionalize things, right? For a computer to work with it, we can't have units running around. And so instead of h bar squared over 2m times s squared, now we're just going to say s squared. Basically, the prefactor is not that important, h bar squared over 2m. Okay, and so, and then in addition, we're also going to let the lattice constant a go to 1 as well. So no dimensions there. So really just the energy is going to be just equal to s squared, where s is the is basically the length of the k vector. Okay, so let me execute that. Okay, fine. Now what I'd like to do is plot those 6 energy curves that we talked about just before. Okay, and so you can see them here. In the plot command, there's 6 entries, right? There is E of S, so that's got to be just our standard parabola where the g vector is just not there. Namely, we've set it to 0. And these two here are for the g vector of plus minus 2 pi over a times I hat, right? Those are the left and right pointing reciprocal lattice vectors. And then these ones here are, this one here is the top and bottom, so the j hat, plus minus j hat, and then here is are the diagonal sets. Okay, so there's just six curves. So you can kind of see that the way I'm doing it here, I'm using a particular implementation here in Mathematica. Basically, I've defined this function as a function of s, and then I'm just putting s plus 2 pi here in the argument, okay, and then here's s minus 2 pi in the argument. So it will get squared, of course, because the function is basically a parabola, okay? So, and then notice what this s does. This s runs from 0 to pi over a, right? And then there's a whole bunch of attributes for that plot command that we don't have to worry about here. Let me just execute that now, and voila, it doesn't take very long. Here is what we get. So you see these 6 traces. Okay. Yes. Very good. So this is path 1. Now we can repeat the whole thing for path 2. And for path 2, just for fun, I tried to mix it up a little bit, and I'm implementing this in Mathematica slightly differently. Okay, so first off, the k vector here is now pi over a comma s, the row vector. Sorry, the row vector pi over a comma s, like we said before. Okay, so here's k2. And then I'm defining 4 of these g vectors. Okay, so you see here is the g vector 2 pi over a I hat. Okay, here is 2 pi over a j hat. Here's the I hat plus j hat, okay, I hat minus j hat, and so on. Each one of those could get a plus or minus in front of it, but I'm not defining 8 of these. I'm just going to take care of the plus minus in here in this next line. So for instance, here I have K2 plus G1, and then I have K2 minus G1 here. This norm command is actually very useful. It comes in very handy right about now, because what it does is it evaluates the length of that vector, the magnitude of the vector. This is a Mathematica command for please evaluate the length of that vector in parentheses in the argument. Okay, and so I'm basically evaluating a whole bunch of magnitudes, and then I'm plugging it into the energy formula where the magnitudes now get squared, right? So that's another way of implementing the same thing. And here I'm plotting basically the 9 curves, okay? Again, S ranges from 0 to pi. What does that look like? Okay, well, let me evaluate this, and then let me execute that as well. And here we go. Here are 9 curves now. Let's see, 1, 2, 3, 4, 5, 6. Some of them fall right on top of one another. So there's some degeneracy here. Okay, but there we go. That is for path 2 going vertically up to meet the corner. And then there's only one path segment left, namely the one that returns you from the corner to the origin diagonally down. And so here, the k vector is going to be s comma s. That's going to be the row vector s comma s. You're going diagonally down, and s will go from pi over a to 0. Okay, so and I'm going to basically be doing the same thing, right? So basically first here, evaluating the various magnitudes of those combinations, and then plugging them into the energy formula, which is basically just squaring those magnitudes. So when we do that, then we get this picture. Okay, so there we go. That's path segment 3. Now what I can do here is I can put them all together in a single graph, right? Superimpose them all, and I get this complicated looking diagram. Or what I could do, and this is more commonly done, I can put them sort of side by side, okay, and we get this particular diagram. Okay, so this is path segment 1, path segment 2, path segment 3. Okay, so that's how we constructed a 2-dimensional energy band diagram. Okay, so basically this is what we got. This is another way of visualizing it here, right? So we went to the right from, and here these 3 points are labeled, you know, capital tau, x and k here. So if we go from tau to x, well, that was our path segment 1, from x to k 2, and from k to tau 3. Okay, and so then we can sort of put this all into these 3 separate graphs into one graph, okay, where we go from tau to x, from x to k, and then back from k to tau. And so this is what we just got in Mathematica. Those 3 separate panels sort of merged into one diagram. Okay, so of course 1 and 2 and 8 and 9, well, those are the same points, aren't they? Because we're back at point tau. Okay, so the point I'm trying to make next here is that we can extend this fairly easily to 3 dimensions. In the end, our real crystals are all going to be, well, yeah, I think it's fair to say that all of them are going to be 3-dimensional. I mean, there's some quasi 2-dimensional and maybe even quasi 1-dimensional materials, especially now with nanofabrication facilities and so on. But most of our materials are three-dimensional. So let's see how this would sort of generalize to 3 dimensions. So here, for instance, is the same thing basically in 3 dimensions. And here I'm looking at a face-centered cubic structure, okay? And of course, our first Brillouin zone, okay, is now a volume, right? And it's depicted over here on the left, sort of this red volume here. The interior of it is our first Brillouin zone. And again, we would like to explore that reciprocal space by going on various journeys, okay? And again, these points, these significant points are labeled here, tau, x, w, l, tau, k, x, and so on. Okay, and so we're basically doing the same thing. Okay, the reciprocal lattice vectors come in as well to generate these various curves, right? And we would just have to know what are these reciprocal lattice vectors for an FCC structure. Okay, but then once we have this set of, these first set of G vectors, then we could use them in the exact same fashion as we just did. And we get something like this. Okay, I don't want to dwell on the details here, but I do want to communicate that this is really fundamentally no different. There's no fundamental difference here between 3 dimensions and what we just did in 2 dimensions. Okay, so take a look here. This is the free electron model, okay? So let's take a look at an actual crystal that has an FCC face-centered cubic structure. And aluminum here comes to mind. Okay, so here is the band structure for aluminum. Okay. So I want you to take a look at this, sort of scan it visually, and then compare it to the free electron model. Okay, so I'm going to go back. Take a look at this diagram down here. Okay, so here's the parabola, up and so on, and then it kind of sort of continues. Here's a sort of a big parabola here. Okay, take a look at that, and then take a look at this. So here and then here. Okay, there are some distortions and some gaps that have opened up and so on. So this is clearly not free electron, but there is a unmistakable resemblance. And this is why sometimes it is useful to start with the free electron band structure, you know, going along with a particular crystalline structure, FCC in this case, because then it sort of informs what we're actually seeing. And so these curves here can be generated using sophisticated models, okay, where you turn on the lattice. So these are theoretical curves, but they can also be measured using, for instance, neutron diffraction. Okay, so these curves can also be experimentally verified, and it's interesting that we get such curves both experimentally and theoretically that really, you know, have quite a bit of resemblance to the free electron bands that we get with this fairly simple analysis. Okay. So I hope this was useful for you. I hope that this made these complicated looking energy band diagrams, band structure diagrams, a little bit less intimidating and a little bit more approachable. Okay, so one thing that oftentimes does appear in such diagrams, in addition to the energy bands, is the Fermi energy. Okay, and so usually a line that is labeled Fermi energy. And so, so if you actually look in our book, that's what you see a lot of times. So that's really our next topic that we need to tackle, is what is up what is the meaning of the Fermi energy. So stay tuned for that.